So welcome everyone to this edition of the Verifiability Talk series. It's my pleasure to introduce Rob Richardson, who is a professor at the Department of Mechanical Engineering at Leeds University. He is an expert in robotics in various aspects of it, and he's someone who knows actually how to build robots, which is very exciting for our project as well. And he'll be exactly talking about that. He'll be talking about robots for the real world. Rob, the floor is yours. Thank you for accepting our invitation.
Fantastic, great pleasure. So I want to, I guess it's a little bit different than a lot of the more theoretical things, but I think it's really important to think about. Of course, this is all towards real robots doing real tasks. So today I'm going to talk a bit about, I guess, some applications of robots and hopefully bring across some of the complexity and some of the challenges of doing it for real. So it's a very different scenario, having, I guess, well, simulations for one thing is one level. The next level being kind of lab robots in a very constrained environment, and then of course the real level is actually robots out into the real world, and that's kind of a really difficult and challenging scenario. So yeah, I'm going to give you a bit of a flavour of the sort of things we've been doing at Leeds. So it's not just Mark, of course, also Baal Kadur and Cheng Zhuzhou, who are also working on this project, be involved in this this work as well. So yeah, so I always like to start from the end. So I'm going to give you a very quick flick of some video stuff of what we have been doing the last few years, and then I'm going to go to more detail. So lots of, as you'll see, lots of physical robot stuff. So bringing things together, taking commercial systems, modifying them, but also just building things properly from scratch for particular applications. I think with all these things, it's interesting to reflect upon as we see them, how we'd actually go around modeling them and simulating them. So mostly we don't do this because it's just too hard and not worth the effort in terms of the outcomes. So you've got things like friction on material, you've got granularity in terms of sand, you've got so many interactions that are just really hard to understand what you do to even flying up there in a confined space, the turbulence is really hard to predict, and the interaction with the environment is very hard to understand. So these are obviously proper real world challenges. Yeah, so just to flavour, give you an idea of the kind of things that are going on. I think one thing that's interesting, one thing I would really want to emphasise, I guess, in our work on the node and generally across the overall hub, is that if we're using exemplars to really try and push them for real applications, the temptation is to kind of try to, I guess, verify things that are not simpler by any means, but that are more doable, perhaps. So of course we have to meet somewhere halfway with this sort of verification thing. Clearly we can't verify the things that are the very complicated things, but yeah, definitely trying to get as close as we can do to real applications, I think, would be really useful. So a lot of work we do at Leeds is on infrastructure. So this slide here just illustrates the kind of different complexity that you might experience. So this is well away from the lab, of course. So you've got, if you look at even just an infrastructure, which is kind of one very small domain of many other bigger domains, you might be working in sewers, you might be working on busy highways, you might be working on bridges, nuclear power stations or even just commercial, just normal houses. And the different types of environment on this are obviously absolutely massive. So even just in doing that is a really interesting kind of example of how a level of complexity in the real world. So in a lab, you have much more control over the environment. Of course, actually, when you're doing things real, it's much more difficult. Another example here of kind of this is a great example of sort of street works. We do a lot of work with the robots to try and repair street works and things. I would love to know what an autonomous car would make of this. I mean, you would hope that it would make sense of it. I'm not sure that I can make sense of it that well. It looks absolutely madness. And of course, there are many places like this, I'm sure. But this is a really good example of the kind of, again, the complexity in the real world that you might expect roads to have some level of, I guess, sense. But I guess in the real world, that doesn't always happen. It can be a bit crazy. So yeah, so robots in the real world. I can hear someone typing. Is that Mohammed?
Sorry, no, I muted. There was a participant.
Okay, it's okay. Sorry, yeah, okay. But yeah, so in terms of the real world, of course, robots have to interact with really complex environments. You have things also perhaps not very obvious, things like energy and battery management. So as battery power fails, performance can change. So if you're trying to verify a system working in a particular environment, it may not behave the same way, even over its standard operating procedures. It may be that as the battery gets halfway through, things start to change, the power starts to change, and so forth. So things can actually be doing that. The sort of work we've been doing is go back. Yeah, so we can land on things, and of course we have also communication sensing. So it's the physical robots, but also how they're communicating to things is also very important, how they're getting commands, how they're doing things. And of course, if we want to move around the environment, we have to make sense of the environment. So it's more than, of course, 20 years ago, it was all about just don't hit things, doing maps and things. Now it's, of course, making sense of the environment and trying to understand what's going on. In terms of a drone, just an example here. This is a. I've got two parts of this particular diagram. This is just an illustration of the kind of complexity that you might get in terms of the physical hardware of a drone. This is a DJI. Well, it's part of a DJI drone potentially, but lots of systems and the controller and so forth. So you have, of course, propeller blades. You have different types of batteries. You have communications. You have the flight controller. On top of here, you probably also have another computer doing the computation for vision or other manipulation. You have sort of course, controllers, and you have gimbals and so forth. So even on a relatively straightforward system like a drone, which are commercially available, there's lots of stuff going on. And so this is really the standard one without the next level. So normally another computer would be on there. That computer will be processing vision or doing decisions that would then control this. So it's really quite a complicated system. And I guess all of these things probably can't be modeled, probably don't need to be modeled and investigated, but just to illustrate the kind of level of difficulty. And even in actually the motors themselves, if you want to understand sort of how things behave, of course, you know, how a certain signal to a certain motor causes a certain change, you need to understand how they're working. And of course, just for this kind of thing here, you have brushless motors. So brushless motors in drones are just coils that are inside magnets, of course, and you have a controller in there. So the real elegance of these modern systems is they are really self-contained packages like plug and play. So the speed controller is nice small controllers. This is what plugs into the motor, makes it kind of working in the right way. So yes, the beauty of it is they are well packaged. Of course, part of this as well, you don't necessarily have full control over things. So in terms of lags, for example, if you're trying to do a stability of a certain control or a certain motion, the delays in terms of thrust are not necessarily known. The flight controller will take some of that and do some kind of calculations and things, but in order to model these things, it can be challenging and quite difficult to do that. Also, so again, the example of drones here, if you have a physical drone, then you may want to modify it to do manipulation, to do things. So here's just some examples here of these are kind of modified things. This is the kind of stuff we're doing at Leeds, where we're taking. So I think some of them are commercial drones. So I think probably these bottoms, this one certainly is a commercial drone. Some are modified drones. Some are very much bespoke, completely bespoke drones. This one here, of course, is a huge system. So in terms of drone technology, we are moving, certainly in a research context, well away from, if you like, conventional just flying around inspecting. It really is what I might call the air and ground interface. So it's drones interacting, picking up, moving, touching, manipulating. I mean, this thing here, of course, is huge. It can lift up chairs. interestingly, of course, this is a nice demonstration, but the reality is this drone, I don't believe, can pick this chair up and pull it forward here. So what's happening here, of course, is that it's able to pick it up reaching down, but the forces are huge if you try and lift it up. So lots of these things, let's go back. Lots of these things look amazing, but of course they're limited. I'm just going to show you, we've done lots of work with drones. We have built our own drone with a manipulator. This is actually the best one I could find of our video. There probably is better videos around. This is our drone here. We built a custom manipulator here. We were doing a trial, which I'll come on to later on, where we were trying to catch a drone, which is probably a bit not the best thing to do. This arm here is quite low dynamics, so really we want much faster dynamics. We're trying to pull a ball off or trying to knock a ball off a drone. But as you'll see, our dynamics of our arm is far too slow here. Yeah, it wasn't successful. And yeah, so as you might expect, we ended up having a collision and lost our drone. One thing that I think is really interesting, which I'll show the video, is the modern drones have absolutely amazing stability and robustness to interaction. So I showed that diagram earlier on where you have a controller and you have, go back, stop doing that. So we have a controller and you have thing that here. When this smaller drone hits it, the larger drone has a little wobble. In fact, it gets a broken blade, so it's lost a blade. I think another motor got hit, and yet just after that, it's probably can't see it. This thing here, it's just like it was before. So that's an amazing robustness, considering it's just lost 1.5 of its actual propellers and thrust. So I guess that's a good example of how we want ideally robots should all behave that way, that they can suffer damage, extraordinary damage, and yet be able to carry on and do things in the right way. Okay, so this is one of our things that we will be looking at, I think, in terms of the node, investigating some of this stuff here. This is one of our drones to repair road surfaces. So what it's doing here is, this is the earlier example. We are able to land and deposit material. So interesting stuff here in terms of recognizing where cracks are, depositing material. So we can carry quite large payloads with drones. We can land on real surfaces. There's definitely huge challenges around understanding what are cracks. That's quite difficult. And also in terms of actually managing the actual weight and payload and things. Let's go here. So our drone is modified. So I mentioned before how we can take commercial systems. So we're using a DJI drone, and then we can actually modify it to make it bespoke and different. So in this case here, we wanted to be able to drive around. So I think it's one of the very few, it might have even been the first in the world to have tracks that function on the ground, as well as flying around. So we can fly around, we can land. This is great because, of course, then we don't have to always fly. We can deposit material, and you can see here we've got this. This is our bespoke made asphalt pouring machine, where we can repair road surfaces. And you can see here it's been built and being assembled and things. So we can have asphalt in here. We can cook asphalt, if you like, or melt asphalt. And we can deposit it into road surfaces with the aim, of course, of actually repairing them. And that's our track, which of course, the thing here, I suppose, shows it's been totally bespoke manufactured. So we're making it from all the base components. Obviously, a simple mechanical example, but still quite challenging to make by itself. I'll show you a video of it driving around. This is actually one of our second iterations here. You can see that we've actually gone away and built this. So yes, it's working. It's actually quite hard because it has to be able to carry quite large weight. Has to be able to support 20 kilograms of weight, whilst being incredibly light itself. So there's lots of engineering going, lots of optimization in terms of making components lighter and all this kind of thing, so they can move around and drive around and be able to do that. So yeah, you can see here we're driving around carrying our different payloads here. Here's an example of it actually working. So I mentioned on the real world. So I think it's whatever we try and do, we should actually do it in the real world. Here we are actually on an asphalt strip depositing the material, and you can see we're repairing this here. So quite a nice example of a real world system that actually could be used and can be done stuff. And I think here we'll just see the again, this is the tracking. So there's lots of vision going on even when we're depositing material here. So even this process here, there's quite a lot of engineering going on here. So we're able to vision track the crack interact with it, manipulate, and we're able to then, you can see here, we're actually driving around and depositing it so that we actually align the material with the crack itself. Even that by itself is not trivial, because actually the cracks aren't that clear. You can see them, it look clear to us, but in a vision system, it's quite hard to understand where that crack is and what's going on. Yeah, so that's one example of things. Stop talking, Rob. Arguing with myself. Yeah, so that's one example of things. Another example of what we did. So we've also been, of course, been developing robots for in city environments. When we had the COVID issue, which of course we still got for a while, unfortunately, we went and we modified lots of our robotic systems to actually be able to disinfect for COVID. So we're looking at how do we create robots that are able to go and actually disinfect and do things. So here I'm going to show you a quick video of some of our work in that area there, disinfecting robots. I'll skip myself forward. That's not worth seeing. That's fine. Yeah. So in an airport environment here, in particular, and also in urban cities, and what we're doing, I'll kill this down. I'll just talk over it actually. So what we're doing is we have this challenge where we need to be able to navigate, of course, in the environment. We need to be able to identify certain features that may be areas of particular touch points, where I'd put it. So this is areas that would be potential for touch points, and then automatically disinfect them. So we have two different types of robots we've been working on. One robot being, as you saw before, which is a ground robot. We've modified it to make it easier to navigate on surfaces. So we actually have two big wheels, and we have casters for the other ones. So these here are quite important. These are, because that helps in mobility. And of course, also a leg robot. So we lots of work with leg robots. As you might expect, we can navigate around, we can build maps of the environment, we can then plan certain places to go, and then we can spray material on it and disinfect it. So spraying, in fact, is I guess one of the simpler tasks. It's more difficult to understand where things are and try and work out, of course, and actually understand where they are, but also plan a path. So you might be able to identify a certain feature, but then you have to plan an interception path that kind of skirts around the object, that can spray the material onto the object. So yeah, it's quite a challenging task to be able to go and do that. And of course, there is an issue in terms of verification. How do we guarantee what we've done? How do we know where we've been? How do we do things? And as an example here, you can see this is some of our stuff to do with image recognition. So we can identify certain features as we go real time, and we can then hone in and try and track down onto a bench or something like that. You can see potted plant person. A lot of these things are already inbuilt in the software we're using in the ROS software. So you can use these packages, which are quite nice to be able to to identify features. I guess in terms of the verification or understanding how you guarantee this sort of behavior, that's obviously really tricky. So I'm sure we'll have challenges around that in terms of the complexity of the things we're using, how open source they are, and how specific we can be about doing certain tasks, which is challenging. Another example of our work we've been doing, we were working internationally just before actually COVID came. We were in the UAE doing the MBZ ISE Grand Challenge. This was actually quite nice, again, to test our robots in real environments. So a lot of the stuff we do is to take them out and to really test them, to understand what they can do. So the challenge we were trying to do, there's lots of challenges we tried to do across there, but one of them was actually firefighting. Another nice real example, especially in high tower blocks, for example, with the drones. Of course, quite topical, hopefully quite a useful application at some point. Potentially, flying around, identifying fires with ground vehicles and air vehicles, and in particular the air vehicles. The ground vehicle, I think, case is not so exciting, but the air vehicle one really is. Potentially, if you've got fires in difficult to get locations, you can definitely spray and do things. So here's one of our drones that we built for this challenge here. So again, another good example of the kind of things we're doing. A large commercial drone that has been modified to have automatic spray thing on here, so we can carry certain amounts of liquid. we can spray it, and we're also able to control the position of it on the end, so we can spray in different directions, and we can actually sort of put out fire. So we can detect the heat. So we have sensors that can detect heat, and also vision sensors. So automatically we can try to track certain features, position the drone in real time, being very careful, of course, not to hit the wall. This is one of the challenges we have, of course, that if you're not careful, you can actually go and you can actually damage or strike things, which of course is a bad thing to do. So we build these systems, we modify them, and then we can deploy them. Example again of some of our stuff here we've done. This is an example of our vision systems here. So we have different things we can look at. So we have thermal images, we have heat sensors here, and we can see from this where features are, and we can automatically try to spray into certain locations. One of the things you can see here, this is obviously the thermal thing. This is kind of the camera stuff, and you can see just about see what we're trying to do. So this is mapped here, and this is mapped here, and we're trying to fuse these data points together to be able to understand the position of the fire and spray it in. This is particularly hard for us because the flame actually is blowing in a different direction, and if you want to get points, we have to shoot it in a hole. So put it in a hole was quite a difficult challenge to do. So it's quite. In the end, we ended up adding offsets and things such that we could actually go away and find the right position for spraying it into the hole. Okay. If you are interested in our work on this MBZ thing, so I'm going to do a bit of a plug here. We recently released a film, which I'm going to show a quick trailer of this now. So it's a 40-50-minute film on our adventures of deploying real robots on the documentary. So I'll just play this quick film to give you a flavour of it. But a bit of a plug, a shameless plug here if you like. But please do go and check it out. I think it's a good video, and hopefully you'll enjoy it.
Rob, I'm not sure whether we hear the voice. So
sorry, say again.
I'm not sure whether we hear the voice from your film.
You can't hear it, can't you?
We can't.
Okay, if I play a bit louder, will that work? Let's try that.
I think you should do something so that it goes through the. No, we can't hear anything.
Okay. I'll just talk over it then. If it doesn't matter if you can't hear. I thought you could hear it, but it's odd because you'd think you'd hear it through my video conferencing, but I guess not. Yeah. Okay. Okay. Well, I'll just play it and talk over it anyway. So let's not worry about that. Yeah. So anyway, I guess I'm just plugging it here anyway. So let's skip that. Let's go on. But yeah, do check it out. It's a fun video, hopefully, and good to watch. So yes, I mean, we've talked a lot about modifying things and so forth. We haven't talked a lot about, I guess, the kind of way we'd go about doing that. So one thing we have in Leeds, we have a facility for physically making robots. So we were quite fortunate about 5 years ago getting funding for this facility. So really lots of state-of-the-art machines that can be used to manufacture components, quite often quite small-scale components. Yeah, we can manufacture things, and of course all of these things are actually available for anyone to use, I should say. So if anyone does want to make any mechanical or any physical parts, we do run it as a small research facility, so you can actually use the machine and actually make stuff. Our challenges for this, let's go back, are in complexity. So how can we add complexity to robot systems? Of course, useful complexity. But if we wanted to make a small walking robot with 30 degrees of freedom, for example, 30 articulations, how could we do that? That's one thing we're trying to do. Of course, miniaturization, making components that are very small is what we're trying to do. We have a theme on 3D integration. This is about trying to make robots that are functional in a truly 3D sense. So normally when you make a robot, you get a circuit board, you get a box, you put the circuit board in the box. But what we're trying to do is really change that process. So effectively, the box is a circuit board. But if you do that, then of course you can have much more things in the same space, which is really useful. And also a theme on minimal assembly. So quite often when you're making robots, especially if you're making small robots, it can be really difficult to actually assemble them. That's by far the hardest part. So you can make incredibly small parts. You can see in this thing here, we can make incredibly small parts. but how do you get these parts and put them together to make some kind of robotic system? That's a challenge. So here's an example of something we made with that process. So we were trying to make a small walking robot, and we wanted to make it with the least possible amount of parts. So you can see here we've got a walking robot here. We wanted to 3D print this system that has actuators and parts. Not actuators, sorry. It has mechanical parts in it, gears and things, but with the fewest number of components. So we ended up with 3 components. But we can 3D print all of these legs, these joints, already attached to the body, already attached to gears. So we end up just having 3 different components that you can actually go away and make this leg robot with. So it's quite a nice example of this. You can see here it walking around. So your top part, bottom part, and added some bits on here. And ordinarily, it'd be really difficult to make this. We'd have to go away and we'd have to assemble small parts and try and screw them together, and it'd be a very difficult process to do that. So you can see here quite clearly, it's the 2 parts, top and bottom, but all of these legs are printed in situ. And it's a more example here of our printing process. So we are able to make things using robots, quite complicated things. And normally 3D printers just make things inside a box, but we can use robot arms to make quite complicated things in different structures that would be done. And actually our current research is to make robots with parts embedded. So you can see here, these components here are interesting, but they're purely plastic components, albeit very complicated shapes. But what we can do, what we are going to try and do is we can make a robot that has the parts inbuilt. So we have actuators, we have sensors, we have other things all printed together in a single box. And then we can actually, the vision really is that we print it and then it walks the bed. So you can imagine like a leg robot. We have this process where we have robot arms handing in motors, we're printing around it all together, and at some point it just walks off the bed. So it's a self-assembly process for quite a large robot, like a dog-sized robot, and it'll just walk off the bed and walk away. I guess maybe a bit science fiction-y, but I think it would be quite fun to do. And we've got another example here of our process here. So what we're doing here is we're trying to fabricate. This is a functional insert. We've got a motor on here, and we're printing a plain body around that motor. So this is one of our first examples of actually embedding components. So we've got the motor in there, the propeller in there, and we're printing an entire plane around the motor, such that it's assembled in one go. And you can see, of course, with 10 times the speed here, we're printing things.
They look so good.
Yeah, like it?
Yeah, it's that plane.
Yeah. So yeah, so we're assembling it in.
Continue watching, looking for my tablet, okay? I'm going to be quiet there.
So yeah, so we can see we're assembling this plane now. And of course, we always do field testing on this. So this was a nice example of the actual testing of the plane. So you can see here we're giving it a good, proper real-world test. As you can see, there's clearly work to be done there. So that's interesting. So we of course, it demonstrates the process of the manufacture, but in fact, as you saw, the dynamics aren't quite there. So we've got to do a lot more work in terms of the dynamics, in terms of actually getting things assembled and working in a certain way. So I've talked a lot about examples of physical things. Of course, I do want to talk a bit more things that are linking, I guess, to how we might go about trying to link some of these examples. I'm sure when you're looking at these things, especially if you're looking at it from a verification point of view, they are all really almost impossible to do right now. How would you verify any part of these systems? So somehow we're going to have to, I guess, is what we're trying to do. So the work package that I'm a part of in this particular node is all about closing the reality gap. How can we get verification closer to some of these systems? I think there's a massive gap there. But yeah, how do we get them closer? So in terms of simulations, so I guess to be frank with you, I think we don't do a lot of simulations. The main reason why we don't do simulations is that the effort to simulate things is more difficult. So even in the example of, say, a leg robot, the effort to kind of really understand how the legs might interact with certain surfaces, be it kind of soil or other things like that, is quite challenging. So yes, we don't do a lot of simulations, but we do sometimes simulate things. Also, one of the things we do quite a lot of is a thing called gazebo. So it's used quite widely in robotics. It's an open access type sort of simulation, and you can put stuff in it. You can do some nice things with GPS, IMUs, and other things like that, to be able to kind of simulate things. I guess it's quite good for if you're looking for autonomy simulation. So I guess there are different levels here. If you're simulating things, you could be simulating the autonomy. But also, of course, I guess from my point of view, a lot of the physical side of things as well. So you're trying to understand how it would really interact with an object or an environment. But it does give a good environment for modelling UAVs and also ground vehicles, which is quite nice. So we can do stuff like we can create CAD models. So CAD model being a computer-aided design module that can actually go away, design the shape and the form of these things, and it can be quite a different, unusual type of thing. We can use the actual ROS, so real world operating system, to be able to link and run it, and we can use predefined environments, and then we can simulate things. So we can do all these things, and we can simulate stuff, which is quite a nice platform. I think especially if you're looking for the autonomy, I say the autonomy is more robust probably to simulate than, say, the physical interaction of things. And here's an example of some work we've been doing. So you saw before our COVID robot. So the COVID robot here, it's a standard robot form. So this is a Husky robot we bought commercially. Another example of how we modified things. So it's a commercial robot, and we've modified. We've been able to put this dynamics into the simulation, so we can see how it moves around here. Yeah.
You've done the work, can you see?
I'll have a look. Yeah. So we understand the dynamics of the robot driving around using the casters. Of course, the output here is very much, like I said, like sort of a SLAM model here, building up things. But it's a nice example of how we can incorporate a standard robot with physically modified with some physical interaction, different kind of dynamics. So what we've done, so basically by changing the wheels here, we've changed the dynamics to being different, and we can enable to simulate it into a real world system. Of course, we can get much more complicated here. We can simulate leg robots. So leg robots, of course, have much greater dynamics. So in this situation here, you can see we do lots of work with leg robots. Chengzu in particular, who's a part of our node, works a lot in leg robots. And you can see here that we can modify it. We've got some kinematics we can put in here. We can design physical robots, different kinds of physical robots, different kinds of shapes, and we can simulate them. And then, of course, we can go from that to prototype. So you can see here, this simulation is quite realistic. I mean, it's a simplified environment. Of course, the ground is particularly is simple. I know Chengzi is very interested in actually trying to model walking on sand. So this is fine for walking on a nice flat surface. But of course, sand dynamics is very difficult. But of course, it's difficult, but also quite common. If you want to have a robot that's patrolling a beach or even walking around certain areas, even mud and things like that, it's not an unusual environment. It's quite standard, quite normal environment. In terms of the aerial side of things, you can also connect it directly to actually robot autopilots. So you can use Gazebo directly in that, and you can then understand sort of, I guess there's a lot of the work. A lot of work we're doing to try and connect the real world things, so you can use the physical hardware and use a Gazebo output to visualize what the hardware is doing, which is quite nice, especially if you're trying to debug the motion and trying to understand how the motion works in certain ways and does certain things. And here's an outcome of Gazebo. You can see here that it's kind of, the graphics are okay. It's sort of cartoon-like graphics, but it's good to illustrate. So I guess one of the things here, it's a really nice way to understand for the human, for us to understand what the robot's doing. But there is definitely the case is that the actual output is not good for doing things like visual feedback. So of course, if you want to simulate a robot making decisions in the real world based upon vision. It can take images, it can look at things, it can catch images of this, but of course we can clearly see that these images are not really representative of what you might actually what you've seen in the real world. So any vision algorithm to process to build models to identify things is not realistic. So that's definitely a challenge of this kind of system here. You can see here, it's obviously more of a blurred thing here, but you can get different images, different directions, but still, of course, very much cartoon-like, very much not really, the detail that we'd ideally want. There are actually lots of different types of ways of doing it. So there's a thing called Simscape. So Simscape uses MATLAB Simulink. And in fact, this is what I would probably be doing if I was doing simulation. Simscape. I would be, because I think it's quite nice to simulate very specific parts of a robot system. So I think to simulate a whole robot is quite difficult. Probably not the kind of the best way, not the simplest thing to do in Simscape. But to understand, for example, a particular robot joint, to understand a particular part of a robot is quite powerful. And it's programmed very much in lower level sort of things. So of course, it's just equations being put in here and stuff. This is an example of a simulation from Simscape. But you can see the kind of we're putting models in here, so we can identify models of components such as motors or planes. We can put them in here. We can add numbers, and then we can actually go away and we can simulate and we can understand what's going on. And actually, a lot of my work, I mean, this has been going on for quite a while. Not Simscape, but Sim Mechanics and Simulink, and a lot of the work I did in the early days was actually simulating things on this, working on doing things like simulating particularly pneumatic actuators, so trying to understand. So a lot of my PhD, in fact, was actually working on simulating particular pneumatic actuators, which is quite difficult. Yeah,
but
here's an example of the outcome.
From my tablet.
Okay, go on then. Go on. Here's an example of the outcome of a simulation. You can see, I mean, again, very much like the gazebo side of things, it's a good representation of, well, it's good to visualize stuff so we can visualize what's going on, but clearly it's not anywhere near a real world rendering simulation of what's going on. So we're able to understand some dynamics, do some simulation, some, I guess, physical dynamic simulation, and even some autonomy sort of side of things, but the output is not so useful. And yeah, it's something called AirSim. This is actually quite a nice thing. This is based upon some game engine stuff. So as I'm sure all of us know, that the quality and the resolution of these game engines. So this is built on the Unreal Engine 4. Not that I'm expert by any means in this kind of simulation side of things, but the quality of the outcome is much greater. So if we are doing things such as trying to put in visual feedback loops, then potentially having a very well rendered environment is good. So we can link it up with things like that to do things. So yes, lots of work done on here. Sort of, I guess, like I mentioned before, because the vision is quite good, you can actually do stuff like learn models, and you can try to build up at least an estimation of a model, which you can then, I guess, verify and improve in the real world, which would be good. And you can do a whole brain in the loop, which is quite nice as well, to link up with different things. And here's an example of the output here. And yeah, I think still it's not at the level of a real system, but it's clearly it's much better rendered, and it's actually quite useful to be able to see what's going on with that. So we can use these to do data. I think we've said most of these things, but yeah. So I think there's different levels of simulation depending on what we're trying to get out of it. And I think, of course, definitely the hardest thing is to simulate such that you can have real world visual feedback. I think that's certainly a very challenging situation. So that's really the end of my talk, just to give you a flavour of something we're doing. I'm going to plug the lab, of course I will do. So we're at Leeds with a Real Robotics lab, and so do check out our webpage and see what we're up to and things, and do follow us. And of course, I actually mentioned before the video, do check the video out. And yes, thanks for your attention. And let's have a chat if you've got time about any questions you might have.
Thank you very much, Rob. It was very exciting to look at the real drones and robots. Are there any questions? We still have 18 minutes for question and answer.
Yes, please.
Yes, please, go ahead.
Rob, thank you very much. Lovely to see the real robots, as you say. How many of these applications, which proportion of the applications you've been working on involve neural networks, machine learning, and how many are traditional control applications?
Yes, I think most of them, I would say, are traditional control. A lot of them actually are quite small, so there's an issue around the computation you can put on them in that case. We don't tend to do a lot of machine learning. We tend to, certainly in terms of autonomous navigation and things, we're doing it, but in terms of learning, I guess as I understand it, real machine learning, as in getting new kinds of models, learning new structures, we don't really do a lot of that kind of stuff. So yeah, it's more kind of, I guess, using using algorithms. We build maps and we do things like that, but in terms of learning new structures, we're not doing that kind of thing.
Okay, thank you.
Okay, Michael has his hands off. Michael.
Yeah, thanks, Rob. So you showed some simulations, some gazebo simulations. Do you have simulations in which you have synthetic humans? Let's say you're, fixing roads and a human wanders across, or anything like that, or is it really a simulation of the vehicle and the environment?
Yeah, so the vehicle environment. I guess one thing we'll hopefully do with this project is link them together. So I can't remember which work package it is, but I think Effie's work in terms of actually linking up some of the models. So I think we would like to have the models of humans that we can then have our models somehow interacting with, I guess, to understand that dynamics of things. Right now, so in terms of our road stuff, it's like urban foxes. The idea is that if anyone comes near, they just scarper away. so we don't want to get close to them, but yeah, it would be interesting to think how we could actually try to do that, how we could link up things that were, yeah.
Does it work with teenagers?
Yeah, so this is going to be interesting.
Okay.
Are there other questions?
Yes.
Okay, thank you very much, Rob. I think with that we come to the end of this talk. In 2 weeks we'll have Ivan Tukin from mathematics, who will talk about robustness of neural networks and machine learning algorithms and mathematical proofs for them. Thank you very much again, Rob, for this very interesting talk, and thank you all for being here, and see you hopefully in 2 weeks with Ivan Tukin's talk. Thank you.
Okay, thanks. Okay. Bye.